Today we are starting Section 5 notes, Community Ecology, which deals with species diversity and richness. So obviously a community structure will include species diversity and distinct niches within that community. At the species level, biodiversity refers to a variety of genotypes, species, or ecosystems present in a particular area. So when we're trying to quantify biodiversity, because obviously scientists, we would like to put numbers to topics, we consider both the number of species in an area and the number of individuals that represent each species. So the number of species is what we would refer to as the species richness, and the number of individuals in a particular species we refer to species evenness. So here I'm going to give you examples. So if we have two communities and both have similar evenness, the one with more species is considered to be more diverse. If two communities have a similar number of all species, the one with a similar percentage of individuals among all species is considered to be more diverse than a community with one very abundant species. So here we have two communities, okay? Community 1 has high species evenness, so there's 25% of each tree, while community 2 has low species evenness. We could see there's way more of this type of pine tree than anything else. Therefore, community 1 is considered to be more diverse than community 2. They both have all of the same types of species, but community 1 is more even within that category. We will use Simpson's Diversity Index to quantify the diversity of a species in a community. So the index that we're using, the Simpson's Diversity Index, incorporates both the number of species in a community and the relative proportion of individuals within each species, which represents a measure of evenness. So using this index, a higher value is going to indicate a more diverse community. So you could see here the index that we're going, or the formula that we're going to use. The diversity index equals 1 minus the sum of n over capital N squared. So here it tells you what everything means. So lowercase n is the total number of organisms a particular species has, and capital N is the total number of organisms of all species in that particular community. Okay, so here we have, in this table, we have community A, community B, and community C. So we're seeing the abundance of each species. So mouse, 50, 20, 34, chipmunk, 30, 20, 33, squirrel, shrew, vole, and then we have the total abundance. So there's 100 organisms in each of these communities, okay? So if we're going to use, to try to figure out which community A, B, or C is the most diverse, we need to use the formula from the prior slide right here. Okay, so here we have the diversity index number equals 1 minus, so we have community A 50, okay, over 100, and then we go to the next one, chipmunk, 30 over 100, squirrel is 10 over 100, shrew is 5, vole is 5. Okay, so all of these, so 50 over 100 squared, this number squared, 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 and you add those numbers all together, and it's 1 minus that number, so we got these numbers here, so 1 minus that number, so community A is 0.645. Remember, the higher the number, the better, the more diverse the community would be. Community B, we have 20, 20, 20, 20, 20, so very even here. So we have our numbers there. So 1 minus 0.2, so our diversity index number is 0.8. And then community C, we can see there's no shrews or voles in this community at all. So we've got 34, 33, and 33 again. So those numbers would equal to this here, and then our diversity index number is 0.67. So we said the higher the number, the greater the diversity. So which one would be the most diverse? Dora the Explorer moment. Right, community B, 0.8 is the highest number. Then which one following community B? Right, community C, 0.67 is higher than 0.64. So the index will produce a higher value for communities that have a higher species richness, and for communities that have a higher species evenness. So what we use this number for is it gives us an objective way really to compare the species diversity of different communities. We can look at communities in different parts of the world. We can even look at communities that change over time. Okay, so moving on to the next topic, let's talk about a habitat versus a niche. So this I feel like you should already know really, but a habitat is the physical setting where a species lives, whereas a niche is a complete description of the role a species plays in an environment, all the living and non-living requirements of the environment that allow a species to survive, grow, and reproduce. So in a niche, the abiotic conditions that a species requires are determined by its range of tolerance. So every organism really, or every species has an ultimate niche that it could have to survive, grow, and reproduce in the most optimal conditions. So that would be here in the middle. So there are areas where it can survive, where it's maybe not the ideal niche, and it's able to survive and grow, but maybe not reproduce the way it would like to optimally. And then on the outside of the niche, they can just really survive and maybe not grow and reproduce. So those areas wouldn't be so great for the species, and they would like to really live at those optimum levels. So here we've got performance and temperature. So a fundamental niche, that is the abiotic conditions in which a species can live can live like optimally. Most species do not live everywhere those ideal conditions are found. And that's because in some areas they are outcompeted for resources by other organisms that also want to occupy that niche. So a lot of organisms within a species will live in what we call the realized niche. So there's a fundamental niche, which is optimal, and then there's the realized niche where that species is actually occupying. So for example, here we have these red-winged blackbirds that live in this area. Okay, so you could read about that here. So this is the red-winged blackbirds provide an example. This bird prefers to nest in vegetation that sticks above the water surface of marshes, including shallow and deep water. However, if yellow-headed blackbirds are present, they drive those black-winged birds away from the center locations because they're better at competing for those locations. So therefore, the red-winged blackbirds live on the edges of the marsh, which we would call its realized niche. Niche generalists, we would say, live under a wide range of abiotic and biotic conditions, but niche specialists live under only a very narrow range of conditions. Species can interact with each other within a community, and how they interact with each other determines the energy and matter flow within that community, which can cause negative effects, positive effects, or neutral effects. Some of the interactions even involve a symbiosis in which two species live in close proximity. A couple of these species interactions, we've got predation, we've got parasitism, herbivory, competition, and within competition we have intra-specific competition, which is among individuals within a single species, and interspecific competition where species compete with different species. Competition over time could lead to niche partitioning because species don't really want to compete with each other. So as they compete with each other, the natural selection really pulls towards the different phenotypes. There are mutualisms where two species end up having a mutual benefit from their interaction. We've got commensalism, where one species will benefit and the other one is neither harmed nor helped. So here is a chart of all of those interactions, and there's a video here as well that you can access should you need more explanation. We often have keystone species that show up in a particular environment or community, and those are the species that help a community from collapsing into a very different collection of species. So beavers would be a good example of a keystone species, and they live throughout North America and construct dams out of branches and mud to convert a flowing stream into non-flowing ponds, and those ponds obviously flood large areas of the forest. The water kills many trees that cannot tolerate flooding. The pond created by the beaver attracts many species with niches that are well adapted to the new habitat, including ducks that feed on pond invertebrates and woodpeckers that feed on insects living under the bark of the dead trees. Thus, despite not being very abundant in that community, a few beavers can completely alter a habitat and the species that can live in that habitat. Because beavers completely transform the environment in which they live, they are often called ecosystem engineers as well. So keystone, think of the field of architecture, and that keystone of the arch is that top stone in the arch that keeps that arch and the structural integrity of that arch. So the presence or absence of a species can obviously affect other species within a community. Could have those effects could be direct effects or they could be indirect effects. So the presence of one species can affect the abundance of another species with no intermediate species involved, which we would call a direct effect. Or we could have a species affecting the abundance of other species by way of one or more intermediate species, which we would call an indirect effect. And the examples are here that you can read about. Communities can experience disturbances that cause changes in species abundance and composition, which we would call succession. In terrestrial communities, a major disturbance can occur from natural causes and can destroy most of all the plants and animals in an area. A disturbance can also be caused by humans. In most cases, the process of succession happens slowly and can take hundreds of years to actually unfold. As a result, biologists have taken advantage of opportunities to follow disturbed areas over long periods of time. Now here is an example of succession in a terrestrial community. This follows the island of Krakatau in Indonesia in a volcanic eruption. So you could read here the year, and then wind dispersed, seed dispersed, and animal dispersed plants coming back into the area. So the pattern of arrival and change over time is an example of succession. Here is another example of how you have a field reduced to nothing, and the crabgrasses would be the first that would come back, and then how it would end up going through succession over time. So this is the terrestrial succession of abandoned farm fields. So this video here goes through that. Then this slide, as I'm running out of time here, is succession in aquatic communities. And that is my last slide. So thank you for watching. Sorry this was a long one. Have a good day.